Well, I'll say good morning to everyone. So last class we were talking about long wavelength interferometry, and we were looking at two wavelengths, 1.06 microns and then 10.6 microns. And so here we showed this these two images here of a terrible diamond turn mirror that was in the shape of a triangle here. Tested it using a helium neon laser at 0.6328 microns. And then the same piece tested at 10.6 microns. And of course there's a ratio of the wavelengths of 16 or so. So our sensitivity is reduced by a factor of 16, and almost everything looks good. Almost everything looks good at 10 microns. In a minute we'll see something that didn't look good at 10 microns. Well, anyway, this gets you to thinking a little bit maybe. In fabrication of optics, and the grinding process is much faster than the polishing process. And so you'd like to do as much of the fabrication grinding and only right at the end, once you get close to the shape you want, right at the end do the polishing. And so it would be good if you could test a surface while it's a ground surface and determine whether it's close to the right shape or not. And there are different ways of testing the ground surface, but interferometry is probably the preferred way. At least by me, it's the preferred way. So if we go to a long enough wavelength, even though we have a rough surface due to the grinding, if we go to a long enough wavelength, the surface is going to look smooth to that wavelength. And so the question is 10.6 microns a long enough wavelength to test typical surfaces that have been ground in the optic shop? So there have been a few papers published on this over the years, and I'll show one in the next view graph, I guess. But in looking at the testing of rough surfaces, people normally assume that the height distribution is a Gaussian distribution. The roughness, anyway, is a Gaussian distribution. And some standard deviation sigma. And so we could write here that oops, I'm missing a parenthesis I see there. We could write here that this would be the probability distribution for this surface, or at least for the high frequency structure. Then there's some overall shape to the surface we're also trying to measure. So we could put this into our height variations, and we could integrate over, we're going to assume that the fringes are much more widely spaced than the high frequency structure that that the surface has. And if you go to, I think this reference right here, we'll go through the derivation here to show that the fringe contrast will be reduced by the surface roughness by an amount that goes as e to the minus 8 pi squared sigma over lambda squared. So it's the RMS roughness in units of wavelengths that really counts here as to how much the fringe contrast is reduced. And so we could make a plot of this. And again, I'm not going to derive this expression, but if you go back here, I think in this paper we derived it. The fringe contrast as a function of surface roughness would look something like this. And so even if we go to something that, say, is a sigma over lambda of 0.1, we still have a fringe contrast of 50% or so. So, if we're talking about visible light, 0.6 microns, a 0.1 here would correspond to a sigma of 0.06 microns. But if we go to a 10 micron wavelength, this would correspond to about a micron here. So this is a theoretical curve. So what I want to show now will be some measurements where we looked at different surfaces And this would be the roughness. It was pretty smooth surface, contrast of 1. And that's looking at the fringes. So again, we're saying that the fringe spacing is large compared to the period of the structure of the roughness. And this is just an output of the detector. But anyway, this shows you can see pretty good contrast fringes here, of course. The roughness becomes larger, 0.32 microns. Now, the contrast was measured to be 0.93, 0.44 microns, 0.87, through here even to sigma 1.44 microns. Well, the fringe contrast is certainly not as good here as up here, but it's still pretty good. And even if we go all the way out to a 1.8 micron sigma for the roughness, we still can see fringes. And the fringe contrast is pretty low, but we still see fringes. So this was the theoretical curve. These were the measurements, and we plot it. And there was such good agreement that I accused the graduate student of fudging the data, but he assures me he did not fudge the data. And it really did agree amazingly well. So a number of people have used this approach for testing optically rough surfaces, or as I say, mirrors in the ground state. And it can greatly speed up the fabrication process. So what I'm going to show in the next slide here is where we had an off-axis parabola in our optic shop in the basement here at Optical Sciences. And it had been measured kind of mechanically the best we could. And we thought it was a pretty good surface. And it was set up in a null test, so if the surface was good, we would get straight, equally spaced fringes. And so we decided to test it, to measure it at 10 microns. And lo and behold, this one on the left is what we saw. Fringes weren't, even though this is at 10 microns, fringes were not quite as straight as we thought. In fact, it was a terrible surface, as you can see. But we could measure it, and so we could then we knew what we had to do to correct the surface. And this, I guess, we really had to work over everything on it. But as time went along, then we were able to make the surface better and better. And these were all, again, testing whether it's just a ground surface, no polish at all, and able to get quite good measurements until you get to close to the right shape, and then you would polish it and test it normally. So it works pretty well. And I don't have any results here to show you, but you can also do the phase shifting of the 10 microns. That also works out very well. And I guess I have one more picture. This is an old picture of an old 10.6 micron interferometer that we had made at Waco many years ago. So this had two outputs. It had a collimated beam here of about 30 centimeters. And so if you were testing infrared transmission optics, you could put the optics in here and test it in transmission. And if you were testing something like this off-axis parabola, where you wanted a diverging beam, there was a second output here of just a diverger lens, and the beam would come out here to go to whatever optics you were testing. So a lot of different wavelengths are used in interferometry, and it's a little harder working when you can't see the light, can't see the radiation, but it's not impossible. So any questions on that? Okay. So that's the end of the 10.6, and the end of that. Well, we're still in chapter 8, but chapter 8 was so large I had to break it up into 2 PowerPoints. Okay, so 8.2.11. Who do we play in basketball tonight? Chico State. Okay. And we won't talk about football, that's for sure. Okay. Star test. So this is a really basic test, very old. And all you're doing, you're taking a point source, or taking a very small source in any case, and you're forming an image of it. And you're looking at that image. And when you look at it, it really, I mean, we'll show some pictures here, but to do this right, we really should have movies. Yeah, someone here should make movies of a star test. Because it's really a dynamic process. You want to see how the image of that point source changes as you look through focus or as you look across the field. And you can learn a fair amount. And we'll even go through some numbers here. But I think for the most part, you probably, with a star test, you're not going to use it to get numbers. You're going to just get a qualitative feel as to how well the system is working. And I think it's a good way. You have maybe some complicated setup where you're testing something and you get some results and you kind of wonder, do these results make sense or not? If you look at the image of a point source, you can often get a pretty good idea, do the test results really make sense or not? And you can detect here 1/100th of a wave of aberration with your naked eye. You may not be able to say, well, it's exactly 0.015 waves of third-order sphericals of whatever, but you can tell if you have a very small 1/100th of a wave of aberration. You want to make sure that you're really magnifying enough that you can see the details. And the last item here I emphasize, because this one got me in trouble once. So you have a point source, and you're looking at that point source with some magnification. You have some type of a telescope, some type of a microscope looking at that image. And you want to make sure that the numerical aperture of this viewing microscope is large enough to collect the entire cone of light from the optics under test. Because I got fooled by that once. I was looking at a system, and I didn't think the system was very good. But when I looked at the star test, it looked pretty good. I looked at the image, and it looked pretty good. And then finally, I realized the real problem was that the little microscope I was using to view the image didn't have a large enough numerical aperture. So I was missing a lot of the light. And so while the system looked good, when I actually put in a different lens to get enough numerical aperture to see all of the light coming from the system under test, I realized, well, it's not a very good optical system after all. So last item here can be pretty key. So we all know the airy disk. We're all experts on the airy disk now. You know that if you have a so-called perfect optics, the image of a point source will be what we call the airy disk. We all know that the diameter of the airy disk, I mean, you probably had a dream about this last night. 2.44 lambda F number is the diameter of the airy disk, okay. And you know that if you put in visible light here, about half a micron or so, this turns out to be about the F number in microns. F10 system, airy disk, 10 micron diameter. And you know the central core contains about 84% of the total light. And these other numbers maybe you don't remember so well, but the 84% is something you should remember. The other thing that is very important here, if I look at this image, as I said, the star test really is a dynamic test. And if I look at this image and I move back and forth along the axis, so I'm looking at the airy disk and then I'm adding or subtracting some focus term. If this is a perfect optical system, the image will be symmetrical on opposite sides of the focus as I look at it. And if this is where I said if you have 1/100th of a wave of third order spherical, you look through focus, you will very easily see that it's not symmetrical on the two sides of focus. You may not be able to tell, just looking at the so-called airy disk, you're not going to tell, do I have any a very, very small amount of aberration or not. But when you probe through focus, you will see right away if it's symmetrical or not. And if it's symmetrical, no aberration. Not symmetrical, you know you have some aberration. Now the next, I'm going to go through some numbers here, and I don't, be truthful, I don't think this is, the numbers I'm going to show are real important, but they're kind of interesting. And so I want to show them. And I can't remember, we may have mentioned this once before, I can't remember for sure. So let's say we have spherical aberration. And so the aberration goes as, however much spherical we have times rho to the fourth. And so I'm normalizing rho as 0 to 1. And I want to find how large the spot size is geometrically. And so, remember epsilon sub rho, or here I write it as epsilon sub y, is minus r over h partial of delta w with respect to y. And at the edge of the pupil here, rho is equal to 1. This will just become minus r over h for delta w sub s, however much spherical I have. And I can write that as minus 8 r over 2h delta w. So h is, 2h is the diameter of the pupil. And so I could write here that the blur diameter is 16, just from here. It's going to be 16 f number, so this is our f number, r over 2h, times however much spherical I have. And if I introduce some defocus, we saw before we can change the size of the blur, and we saw that the minimum blur, if you remember this, as we introduce defocus, would be a quarter of this blur. So the minimum blur diameter goes as 4 times the f number of the beam times however much spherical we have. And so the dimensions here would be whatever the dimensions for spherical is. So let's say, wavelength. So it would be 4 f number times so many waves. Okay. So that's for spherical. 4 f number delta w. Remember that. Remember, 4 is my favorite number, f number delta w. Now we go to astigmatism. Well, we could write this as delta w astigmatism times y squared. And again, we're going to normalize this to 1 at the edge of the pupil. And so the transverse aberration is minus r over h partial delta w with respect to y. And so it becomes minus r over h 2y delta w sub a. And so minus 4 r over 2h delta w sub a. So 2 times that would be 8. So the blur diameter here is 8 f number delta w astigmatism. And remember we have 2 line foci. And so this is the length of the one. If we go in between the 2 line foci, we get a diameter, or least confusion, of a half of this. So the minimum blur diameter is 4 f number times however much astigmatism we have. Kind of interesting. Here it was 4 f number times how much spherical. Now it's 4 f number times however much astigmatism we have. So the next, Coma. Guess what the answer is going to be. Okay. So anyway, we write down our expression for Coma here. Delta w sub c, x squared plus y squared times y. We take find epsilon sub y minus r over h partial delta w with respect to y. Go through all that, and we get minus r over h delta w for Coma, rho squared plus 2y squared, and y squared is equal to 1. This becomes minus 6 f number delta w Coma. The sagittal Coma here is 1/3 of that. And so the diameter of the blur circle then would be 4 f number delta w Coma. And so again we get 4 f number delta w. So it's kind of interesting. These all turned out to be the same. Well, I had to look for the right thing here to get the 4, but turns out to be the same. Anyway, I don't know that you'll ever use this, but I just thought it's kind of interesting for that. The other thing that's kind of interesting is to look at the ratio of the geometrical blur to the area disk diameter. So we said, well, geometrical blur, we always got 4 F number times when we had spherical or coma or astigmatism times a delta W here. Area disk diameter 2.44 lambda F number. And so we just take this ratio here and we get a 1.6 times delta W over lambda. And I don't know that I care too much about that 1.6, but the thing is that this ratio, I always thought this was kind of interesting. This ratio of the geometrical blur diameter to the area disk diameter is proportional to the amount of aberration I have in units of wavelength. I thought that's kind of interesting. And I don't know if I've ever made use of that in my life, but I found it kind of interesting to think about. Okay, so what I want to do now is to look at some of the images of point sources. And since you know that spherical is my favorite aberration, we're going to look at that. But before I get to spherical, I have to look at defocus. And so what we have here, well, first off, I'll say where I got these pictures. So I stole them. These 2 books, I just love them. The Atlas of Optical Phenomena by, well, François is the only one of the 3 I knew, but François and others. This is from volume 1, which I told you, we used to have it in a library here. I think someone liked it even better than I did, so they stole it. But before they stole it, I scanned it, so I have it. So I have the pictures. And volume 2 I own and have in my safe at home, or at least my bookshelves at home. So I don't know how well you can see that. You can maybe see it okay. So here's our, well, first off, this is no aberration. So here's our area disk. Now I go inside, inside and outside of focus, same distance, and these 2 patterns are identical. I go farther, identical. Farther, identical. Oops, identical. And so that's the whole point here, is that if you have no aberration, this is very, very symmetrical inside and outside of focus. And if you just have a little bit, you'll see a change. I mean, it really is so sensitive to that. How many of you have looked at a star image like this? Oh, someone must have, yeah. Okay. It's awfully hard to get this. It's awfully hard to get something with no aberration. But these, I know that what I like about this, I mean, these are not computer simulations. In fact, this book was so old that they couldn't do computer simulations. But I mean, these are actual photographs that they took. Now let's look at this in a little more detail. We're going to look at the area disk, and then we're going to look at a couple more of these. So here's our area disk. So you see, 84% of the light is within this little region here. See our rings very nicely. And then we introduce a little bit of defocus. I listen a wave, and it gets something like this. And then with, as we've said so many times, the one wave of defocus, we get a dark spot on axis. And lo and behold, I mean, you really do see that. It really, really works. Okay. So I kind of always like those pictures. Now here, I had to go to my favorite aberration. I know it's not yours, but mine is third order spherical. And so we're going to look here. And I don't know how well you can see that from your seat. But first off, it's not symmetrical at all. It changes quite different whether you're inside or outside of focus. And we'll look at some of these pictures in more detail right here. So that's at paraxial focus. And small distance inside of paraxial focus. And then as we're moving towards marginal focus, pattern like this, and then at marginal focus, something like that. Okay, kind of pretty. So what are we going to look at next? Of course, Coma. Look at this Coma, isn't that beautiful? 2.5 waves of Coma, 1 wave, 6 waves. So we said earlier when we talked about aberrations, what was this angle here? Geometrically, this angle is 60 degrees. And it's pretty close to that. I mean, geometrically did a pretty good job of predicting this. But geometrically, we didn't predict all of this structure inside of here. All of this interference pattern that we see. And I mean, you really do see this in Coma. It's very, very, if you have quasi-monochromatic light, you'll see this very nicely here. Beautiful. See, now aren't you glad you went into optics so you can see things like that? Okay. So, now we have to go to astigmatism. So this is close to a quarter wave of astigmatism, and you see a little bit of something here. 1.5 waves, 7 waves. So, I mean, you get the line that you predict geometrically, but geometrically you don't predict all this other structure out in here. So this is at one of the line foci. And if we go to the circle of least confusion, well, it's not a real circle, I guess I'd have to say. But isn't that kind of neat here? So again, about a quarter wave, 1.6, so close to what we had there. And then 7 waves up here. So some beautiful, beautiful patterns. So this is all for quasi-monochromatic light. And unfortunately, I don't have pictures here for the chromatic aberration, but you get some really beautiful images if you have chromatic aberration. And years ago, there was a student who got so excited about chromatic aberration, he took a lot of pictures, and he gave me copies of them. And some way I've lost them over the years, which I'm sorry I've done. You really get some beautiful pictures. And again, this is where what we should do now is make some movies of this. I was thinking about that. Just make some movies as we go in and out of focus and so on, and you would see the nice colors. So we have longitudinal chromatic aberration, and then we have transverse or lateral chromatic aberration. So you have a lateral separation of the images for the different wavelengths. And I guess that's everything I'll say about chromatic, but you certainly could see some beautiful, beautiful images here. Okay, so that is the star test. And again, you probably don't use it to put numbers, but it's a nice way to check whether the numbers you are getting from your interferometer or whatever test you're using, see if they make sense or not, just by looking at the image of a small source. And I say small source. How small would the source have to be for this to work? Well, you could think of, you want something that is smaller than what the airy disk would be. because you really are convolving your airy disk with your geometrical image. So you want something that is smaller than what the airy disk would be when imaged in image space. Okay, Shack-Hartman test. So, and I left an N off of there. Got it right down here, but I left an N off. Have to fix that. Well, before Shack, there was a Hartman test. And the Hartman test used to be widely used by astronomers. And even as late as in the 70s or early 80s, it was widely used for the testing of large optics. And the way that the classical approach was, you had a large mirror, and then you had a screen that had little holes in it. And maybe we'll worry in a second about how large these holes might be. But it had little holes in it, and you'd put that in front of the mirror. And I remember seeing one of these Hartman screens. I don't remember seeing one at Optical Sciences, but over at Kitt Peak they had, I remember seeing one. So the screen would be larger, or at least as large as the mirror you're testing. And in the screen they had over there, the holes were maybe an inch in diameter. And what you would do is you would, I've left off some beam splitters and stuff here, but you would send light up to this mirror, and the light that went through the holes would come back here. And let's say this is where if we sent in maybe if this were a parabola, let's say, we would go out to the paraxial center of curvature and have a source going up here, and the rays would come back. And inside, and if this were a parabola, it wouldn't be a unique focus, but the light would be spread out. The focus would be spread along here a little bit. And inside of that focus, they would put a photographic plate. And outside of the focus, they would put a photographic plate. And so you could kind of think of these little rays as coming along here, and you would see where they would intersect the plates. And by knowing the separation between the plates and measuring the positions of these spots, you could determine the angle of these rays. And I'll come back to this picture in a second, but this is an actual photograph, well, an image of a photograph anyway, that was before. I think this was taken by a man by the name of Mitch Ruda when he was a student here, but I'm not 100% sure. And the mirror had a hole in the center of it. And if we were outside of the paraxial center of curvature, so we're out here, the pattern for a parabola would look like this. And inside it would look like this. So you would take these photographs, you would put it on some type of comparator, measure the positions of these spots, and from that information, knowing how far apart they were, measuring position of the spots, you could determine the angles of the rays. And then you could compare that with what you wanted, and you could determine if your parabola was good or not. Now, if I look at this, and I look at this, so I claim that's inside, and that's outside. Could that be wrong or not? Let's think. So if I have a parabola, remember a parabola is that curved more or less than a sphere? Do you remember? Turns out it's less. A sphere would come over here. A parabola is less. So at the edge, the light, at the center here, the center of curvature is here. At the edge, the center of curvature is back here someplace. And so when I get to this plate, at the edge, the beams won't be as far out as they would be for a sphere. And now up here, they'd be out more. So I think I do have these right. So at the edge, things are not as far out. And inside, at the edge, they're out more. So I have it right. Now, I don't know. Yeah, I can see it up here. You probably can't see it. But we sort of have around each one of these, we have an area disk. We have the diffraction pattern of whatever this little aperture is. And so it's a little area disk. And so, you know, if we make this aperture too small, the size of that area disk is going to get too large. If we make the aperture too large, well, two bad things are going to happen. One is, you know, this is going to become much larger than the area disk just because of geometry. Plus, behind that little hole, the shape is changing some, and so that's going to tend to blur this out a little bit too. So to make the holes about the right size, you would say, well, you calculate what the area disk diameter would be here, and you calculate the geometrical diameter of the beam, and you set these equal, and that will give you about the size that the hole should be. Okay. Now, why did astronomers like this? If I go back to before interferometry became so widely used for testing large mirrors. Well, they liked it for a couple of reasons. They liked it because it's cheap. Okay. Now, I think there's so much money in astronomy now, but if I go back 40 years or so, there wasn't so much money in astronomy. And this was a pretty inexpensive test. Now, there's a fair amount of work involved in measuring the positions of all these, but in astronomy, you always have all these graduate students, so they can do the work for you. So that was one thing, that the price was low. How about air turbulence or vibration? Did that bother you very much here? And the interesting thing is air turbulence, let's worry about air turbulence in particular. Air turbulence would cause these little spots to blur out a little bit, but if you made a long exposure, you know, things would kind of average out. The spot would become larger, but as long as I measured the centroid of the spot, it still was a good test. So, you know, astronomers really did like this. Low cost, vibration wasn't too critical. Air turbulence, as long as you made a long exposure, wasn't too critical either. So that was nice. Well, back, you know, Roland Shack, who I keep talking about how smart I thought he was. When I first met him, one of the first things he told me was that he had this idea for replacing that screen with a lenslet array. So back here is some optical system we're testing, and I don't care what it is, and you put in some optics to get a plane wave. And then you would put in this little lenslet array. And back when Roland Shack first told this to me, then he would put a piece of film right here. Okay. And so this would be his Hartmann test. And he was very proud of this. He was really proud that he could make these lenses. He'd figured out a way of he could buy some cylindrical lenses, an array of cylinders, and he would put two of these crossed, and that would give him the little spherical lenses he wanted. But did he publish it? Let's see. Well, you know, right there's his publication. I guess like normal for Roland Shack, he wrote it down on a piece of paper and he put it in his file cabinet. And I don't have the location of his file cabinet, although I now have his office. But, well, he was in a different office back then. But anyway, he did not publish it. I think he later had a student who published something on it. But this was a really great idea. As time went along and solid-state detector arrays came out, then other people began using his approach. and they renamed the Hartman test to the Shack-Hartman test. And this has now become not so much for testing of mirrors, but for an adaptive optic system. And so now, let's say we want to correct for the atmospheric turbulence, and so we would have a telescope, light from the telescope coming down, collimate it, send it through here, solid state detector array, and as the turbulence changes, these spots will move around, but we can keep track of where they are. And from that, we get the wavefront slope. We can integrate that to get the wavefront. And then we go back and we make a little deformable mirror, maybe a piezoelectric mirror of some type, of little transducers that we can change the shape of the mirror to correct for the atmospheric turbulence. And this has become a very popular sensor for adaptive optics. This is just looking at some lenslets for the Shack-Hartman test. And then I have two movies here that I stole from someplace. I think it was the Imperial College website, but I can't find it anymore, so I can't give them proper credit. I want to go back. I'll start these over because So what we're going to see on the left, these are the focus spots from a Shack-Hartman test. And you can see them dancing around by the atmosphere. That's kind of neat. And over on the right, this is just something different, but I liked it. This is a stellar speckle image. So this is an image of a star. We're using quasi-monochromatic light, so we see kind of a little speckle pattern in there. And because of the atmosphere, the image is moving around, but also the speckles are changing as the atmosphere changes. And kind of liked that when I found it. So we'll go on just for a second here. So again, I think I took these from the Imperial College website, but they're not up there anymore, and so I can't give them proper credit for it. So kind of the final comments here on the Shack-Hartman test. As I said, whether it's Shack-Hartman or Hartman, their air turbulence will average out as the integration time is long compared to the period of turbulence. But if you want to measure what the turbulence is, you just take shorter exposures, and you can measure the effect of the turbulence. And I guess I said this often before down here, that the holes should be large enough so diffraction doesn't limit the measurement, but not so large that surface errors are averaged out, or not so large that the spot just becomes too large because of the size of the beam. And the Shack-Hartman test has become the wavefront sensor in adaptive optics. Has anyone here done a Hartman or Shack-Hartman test? Shack-Hartman? Testing a mirror?
I did both actually. So Shack-Hartman for testing, using it for a deformable mirror.
Deformable mirror. Mm-hmm.
And
Mm-hmm. Well, that's probably what Shack has become most famous for now, was this particular test. And again, it's interesting that when he came up with the idea, it wasn't used much for 20 years or more. And then when the solid state detector arrays became available in computers and stuff, then I think first the people at the European Southern Observatory began using it, and then other people began using it a lot. Okay, so the next topic here is the knife edge test. And I have to confess, every time I teach this course, I think, well, do I really want to talk about the knife edge test or not? Because, I would never test in optics anymore using a knife edge test. At least not to get numbers. But it is so widely known, and I say I would never test optics with a knife edge test, that maybe that's not quite true, because if you want to determine just do I have any steep zones or not, boy, this is a great way to determine it very easily. And you don't, again, you're not going to put numbers on it, although, I'm going to go through here and show you some equations and stuff, but It's more of a qualitative test. A good optician now, you know, an old good optician, or a good old optician, maybe I should say, might still use a knife edge test, but it's not so widely used anymore. But I think we have to spend at least a few minutes talking about it here. So we start off with a source here, and it could be a point source, or it could be a slit source, where if I'm going to image that source down here and move a knife edge in. So I want the slit to be narrow in this direction, but it could come out of the screen here, but narrow in the screen itself. So what we're going to do is we're going to, whatever the optics is, we're going to image it here. We're going to take the image and we're going to cut across it with a knife edge, probably a razor blade, and we're going to look at the shadows that we generate when we do a knife edge test. Have any of you done a knife edge test? Or you looked at knife edge patterns in lab or, yeah. So if we have, so really what we're measuring here again will be slopes. And it's slopes in the, you know, a direction in the screen here. We're cutting in this way. And if I'm testing something that has a perfect spherical wave, and you cut across here, you're going to get nice patterns here. You know, if I'm inside of the focus, and this pattern is as seen back on the mirror, not as seen here, but as seen back on the mirror. If I cut in here, looking back on the mirror, it's going to be cutting in this way. If I'm outside of focus, well, if I cut in this way, then the shadows are going to be moving down in the opposite direction. So we can easily tell if we're inside focus or outside focus depending on which way the shadows move. And if we're right at focus, well, whatever happens real fast as we cut through the focus. Now, I'm going to go through some equations here. And again, I probably would never use these equations in a knife edge test. It'd probably be more of a qualitative feel for me. But it's kind of interesting to see the equations, and let's do it. So we start off with my favorite aberration, third order spherical. And so we have the spherical aberration term, and then we have something due to defocus. And these are just the equations that we saw several chapters ago. And so how far we are from focus is epsilon sub z, and h is the radius, semi-diameter of the beam, and r is the distance we are away. X and y are coordinates in the pupil. Normalized here to 1 at the edge. So I'm going to find a transverse aberration, so I'm going to find minus r over h partial delta w with respect to y. So we just take the derivative here and we get this mess right here. And so that will give us a transverse aberration. Now at the edge of this shadow, edge of the knife edge, we're saying, well, d is the distance the knife edge is from the axis. And so I'm going to set this transverse aberration equal to d, the distance we are from the edge. And if at the beginning, let's say the knife edge is right on axis, so d is equal to 0, well, the solutions here are y is equal to 0, and the other solution is x squared plus y squared is equal to this mess over here. So what we have here, if the knife edge is on axis, and I'm moving the knife edge along, so epsilon sub z varies here, so I'm moving longitudinally along. The solutions that give me the equations describing the shadow, at the edge of the shadow, are, well, this is a straight line, and this is a circle. So the shadows are going to be, straight lines and circles. So let's look at an actual photograph, which I guess, again, came from this book by Franzone and others. So if I'm near the paraxial focus. Well, one solution was a straight line. There's my straight line. And the other was a circle here. So if I'm at or close to the paraxial focus, the size of the circle is small. Epsilon sub z is small, so rho is small. So the size of the circle is small. And I get dark here. And it doesn't look too much, but dark right there. As I move farther away from paraxial focus, this circle becomes larger. I mean, epsilon sub z becomes larger, so this circle becomes larger. So there's my line. Circle, dark, dark here. Okay? And if I'm right, very, very close to the marginal focus, then the circle is way out at the edge of the pupil here, and that's what I see for a shadow. Now, geometrically, I mean, these shadows are really sharp. In practice, they're a little fuzzy. And that's going to be a problem with this, is that these are, it is a little fuzzy right here. And, I mean, sometimes it can be very fuzzy. And so our whole idea here, if I wanted to put numbers on this, would be that I would measure rho as a function of epsilon sub z, and then I could determine for how much aberration I have, how much third order spherical, as long as I know h and r. And to do that, then I really have to measure the radius of the shadow very precisely. And you normally don't do that. You just kind of look at it and get a feel as to whether it's good or bad. So that was for the knife edge on axis. If I move the knife edge off axis, then D has some value. And we could calculate what the shadows look like. And they would look something like this. So this is A is, knife edge inside of the focus here, ahead of marginal focus, and off axis a little bit. Shadow looked like that. And B was behind paraxial focus. And the shadow looked like this. Okay. Coma, same idea. I go through here. We write down our expression for coma. So W131 y naught y times x squared plus y squared. And then we have our defocus term. Something goes as x squared plus y squared times epsilon sub z times these other factors. Okay, so now this is not rotationally symmetric. The spherical was. So I have to worry both about knife edge parallel to the x-axis and knife edge parallel to the y-axis. And so parallel to the x-axis, I want to find partial delta w with respect to y. So epsilon sub y, I set this epsilon sub y equal to d, and I get this mess over here. I mean, it's easy to do, but I get this mess. And I look at this equation and say, oh man, that's an ellipse, okay? An x squared plus a 3y squared, so that's an ellipse. And then I have something out here that has a y term in it. If I make the knife edge parallel to the y-axis, now I have to find partial delta w with respect to x. And I get this mess right here. And I get something that goes as x times y. And I think about that for a second and say, oh, that's a hyperbola. So for third order coma, we're going to get ellipses and hyperbolas. Kind of remember that. We're going to see that not only with the knife edge test, but with some other tests coming up. We get ellipses and we get hyperbolas. What do the patterns look like? Well, these are calculated patterns. Knife edge parallel to the x-axis. Inside of paraxial focus, I get this. At paraxial focus, I get that. Knife edge parallel to the y. So these are ellipses. Knife edge parallel to the y-axis. Inside paraxial focus, I get something like this. At paraxial focus, it's symmetrical here. I get something like this. And these are hyperbolas. So ellipses and hyperbolas. Okay. Should remember that. Third order astigmatism. This is kind of confusing here. Third order astigmatism. I have something W222 y naught squared times y squared. And then I have my defocus term here. So I get a y squared plus another term that goes as x squared plus y squared. If I put the knife edge parallel to either the x or the y-axis, I'm going to get some, an epsilon sub x and epsilon sub y. So epsilon sub y first, I partial delta w expect to y, and I get this mess here. I'll read it out because there's a minus sign out in front, but 2r over h, w222 y naught squared plus epsilon sub z h over r times y. So I get something that goes as y. Epsilon partial delta w with respect to x, I get a minus epsilon sub z h over r times x. So I get something that goes as x, something that goes as y. Straight lines. But if I have only defocus, if I have no astigmatism, I still get straight lines. And so how do I know if this is a perfect spherical wavefront or if I have astigmatism? And the problem is that if I make the knife edge parallel to either the x-axis or the y-axis, I can't tell if I have astigmatism or if I just have a spherical wave. And so the trick you do here, and you're going to see this trick in some other tests too, the trick we do is we're going to put the knife edge in at some angle to the x-axis. I don't want to make it parallel to the x-axis. I don't want to make it parallel to the y-axis. I want to make it at some other angle. So I'm going to go on to the next slide, and then I'll come back and look at what we have down here. So next slide. Okay, so here's my epsilon sub x and epsilon sub y. Here's my knife edge. So my knife is coming in at an angle. It's not very clear, but this alpha is this angle right there. Okay, so that's alpha. So this knife edge is, it's a straight line. And the equation of a straight line is y is equal to mx plus b. So for this right here, I would have epsilon sub y is m, the slope of this line, times epsilon sub x plus b, b being the intercept here. When epsilon sub x is 0, it's the y-intercept. The slope here of this line, well, this is at an angle alpha here, so the slope is sine alpha over cosine alpha. And this y-intercept here, b, well, I think that's alpha there, so that's alpha there. So the cosine of alpha is d over b. That's the cosine of alpha. So I can rewrite this expression as epsilon sub y is epsilon sub x times sine alpha over cosine alpha plus b is d over cosine alpha. So it's this. And so I can solve this for d, that d here is epsilon sub y cosine alpha minus epsilon sub x sine alpha. So we go back to this. So that's just copying that equation over. And so I'm putting this in at some angle alpha. And so now I have to put in what the epsilon sub x are and epsilon sub y. So that comes from up here. And I get that d is epsilon sub z h over r x sine alpha minus this mess here times the cosine of alpha. And so as I move this knife edge along the axis, what I'm doing, I'm changing epsilon sub z. And so I'm always getting a straight line, but the straight line is going to rotate as I move along the axis. As I move the knife edge along the axis, the shadow will rotate. If I had only a nice spherical wave, I'd get a straight line, but it wouldn't rotate. But because of the astigmatism right here, it will rotate. So if I put in, no astigmatism, this w would be 0, and I just have this straight line, that angle wouldn't change. But now it's going to change. And so what I will see then as I move along here is that the angle will change. Okay? Kind of interesting. So, comments on the knife edge test. Why do people like it? Well, it's simple and cheap. Okay. Disadvantage. It's sensitive to slopes, not the wavefront. So, well, okay. I can do some integration process maybe. It measures the slope in a single direction with a single orientation of the knife edge. So if I really wanted to measure aberrations, I would probably put the knife edge. I would use two different knife edges at two different angles. But well, it's possible to get numbers from knife edge test. You're not going to probably bother to do it. It's a good qualitative test. And if you have any slope errors at all, I mean, you're going to see shadows that are going to tell you these slope errors. It is going to be so sensitive. It's just, I've had cases where I've tested something with an interferometer and I don't see the slope errors. I test it with a knife edge test. Oh, there are slope errors. And then I go back and look at the interferogram and say, oh, yeah, now I see them, But it's very, 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 very sensitive to slope errors, steep slopes. This last paragraph, what does that say? An improvement would be a phased knife edge, which should be which. I found 3 errors in the notes today. Which transmits both sides with a phase difference between the two halves of 180 degrees. Diffraction pattern is symmetrical and the boundary centers are easier to determine. So what am I saying here? This is actually something kind of interesting. So let's look at a knife edge test. And these are our calculations of the diffraction pattern due to a knife edge. And so this is just kind of looking at the intensity you get. And this is a plot of the amplitude. And this is a plot of the intensity, irradiance. So this dashed line right here is the geometrical shadow. And so, the calculations we did above were finding the location of this geometrical shadow. But if I look at the knife edge, it's kind of fuzzy. The edge is fuzzy here. I look down here, the edge is fuzzy. And how do I look at this pattern here and say, oh, that's the geometrical shadow right there? You just can't do it very well. So again, Shack had this idea. He said, well, the knife edge test is always done with a razor blade, basically, where it's transparent and it's opaque. So what Shack said, let's make a knife edge. Well, the whole thing is transparent. But there's a 180-degree phase shift between the two sides of the knife. Okay. Now we're going to use quasi-monochromatic light, so it's truly a 180-degree phase change. He says that's going to give us a much better indication of where this geometrical shadow is. So let's think, how does that work? So I want to calculate what does the diffraction pattern look like for this phase knife edge. So do you understand what I'm talking about with the phase knife edge? Okay. Well, I'm going to use Babinet's principle to do this. I'm going to calculate, a knife edge on one side. I'll calculate what the amplitude looks like. Knife edge on the other side, opaque one here, calculating what the diffraction pattern looks like. So I'm getting these two diffraction patterns. And if this is a phased knife edge, then these two are 180 degrees out of phase. And so in amplitude, I would subtract one from the other one. And in amplitude, you're going to get something like this. And in intensity, I'm going to get something like this. I get a 0 right where that geometrical shadow is. It's symmetrical on the two sides. But if it's truly a 180-degree difference between the two, I'm going to get a 0 right there. And the diffraction pattern would look like this. And this is where my geometrical shadow is. follow that? So this will be much easier. This is much easier to see than this right here, kind of fuzzy. This is very symmetrical, and right there is geometrical shadow. So if I really wanted to get numbers, this is probably a better knife edge. The phase knife edge would be better than a density knife edge. Question?
With the subtraction of those two, do you subtract one from the other and then cross the zero, take the absolute value or something? When you read
Well, I would, in amplitude, I would subtract one from the other one. And they're equal right here, and so it goes to 0. And then I square that to get the intensity. So it's just using Babinet's principle. I know I have two knife edges. I calculate the amplitude for diffraction pattern for one. I get this. You know, I'm thinking of two density ones. I would get this, and I get this for the other one. Now, these are amplitudes, so I have to add these two, but they're 180 degrees out of phase, and so it's really subtracting. And so I'd end up with something like this.
Okay, I was just, you're always writing the amplitude positive.
Mm-hmm.
All right,
Yeah.
I was just looking at the subtraction of the plot.
There may be a phase or something in here, but okay. So let's say I mess up on this and it's not 180 degrees between the two sides, it's 152 degrees. How is this pattern going to change? Well, is it going to go to 0 if these two halves are out of phase by 152 degrees? The answer is no, it's not going to go to 0 anymore, but it still is going to be symmetrical. So this may not be as dark if it's not truly 180 degrees, but it still will be symmetrical. So I still can determine where that geometrical shadow is. Well, anyway, this was Shack's idea, and you can guess where Shack published it, in his file cabinet. And I don't know of anyone who's made one of these, although I've thought about it many times, but I haven't made one. And I don't know if this is ever published anyplace or not. But I thought it's kind of cute. I mean, I like diffraction and kind of a cute idea. A way of maybe, you know, if you really wanted to get numbers from a knife edge test, maybe this is a way to get a little better numbers. Okay, well that's everything I was going to say about the knife edge test. Any questions? Well, I'm going to now talk about the first cousin of the knife edge test, the wire test. So the wire test is the same as a knife edge test, except the knife edge is replaced with a wire. And normally, when we've done this in a lab, instead of using a wire, I can't do it anymore, but I used to be able to pull the hair out of my head, and that would be the wire. So I'd have to get help from someone here to do the wire test now. And so we're going to get shadows, you know, like we did for the knife edge test, but it's going to be the shadow not of a knife edge, it's going to be a shadow of a wire. And all the equations we went through with the knife edge test to determine the shape of the shadow of the knife edge, you know, we have the same results here. The location of that shadow is the same. And so if I have third order spherical, and if my wire is on axis, I'm going to get straight lines and I'm going to get circles. If I'm at paraxial focus, get a straight line, I'm going to get a small circle. So I move away from paraxial focus, the diameter of the circle is going to increase. Farther away, increasing, increasing, until I get to marginal focus, then the circle is right at the edge. So the shadow is showing me You know, what rays am I blocking? Where on the pupil are the rays coming from that are being blocked by the wire? Now, the wire test, I mean, these shadows are pretty distinct, and they're easier to measure the location of the shadows than it was for the knife edge test. So again, for quantitative measurements, it's probably better than a knife edge test. For qualitative measurements, it's not as good, and it's not, you know, it's not used very much, but it's kind of interesting to think about for a minute anyway. Spherical, but I move the wire off axis. You know, you have same equations that we had before, and you just, I mean, you're going to get patterns that look like this. So, on axis, small displacement off axis, and a larger displacement off axis. And I think these drawings here actually came from Shack originally. Now these are just drawings. What do we see in real life if I'm testing something? And this next picture I love, and I don't know who to give credit for this. But this was looking at a parabolic mirror, tested center of curvature, so you see spherical aberration. And this is an actual photograph of a wire test. So here's my circle, and here's my straight line, and there's my hole in the center of the mirror. Now let's look at this a little bit closer up. And lo and behold, oh, this is beautiful. I don't know how well you can see from your seat. Well, at least this is sort of an image of an image maybe, but you get a nice diffraction pattern here. You see the center here, and then you see the, you know, the nice diffraction pattern across here. Very nice picture, I think. So comments on the wire test are, well, I said it already, I guess. It's probably better for quantitative measurements, but not as good for qualitative measurements. You don't really see the steep zones. You don't really get such a good feel as you do with a knife edge test, but you certainly can get, you can measure the positions of the shadows better. Okay, so I guess my time is about up here. So what we're going to do next class is we're going to repeat the wire test, but we're going to use a lot of wires. And we're going to call it a Rankine test. And then after the Rankine test, we're going to see a Rankine test is a little bit like a lateral shear interferometer. So after the Rankine test, we're going to talk about shearing interferometers. So I'll see you bright and early Thursday morning. And don't forget to vote, okay?